All right, so here's a little walkthrough on torque and levers. This will be linked to the torque and lever sort of self-grading quiz. So let's get cracking. All right, first up, here's a pretty classic torque and force question. So we've got a diagram here that's sort of laying out what's going on. We've got a wheel. It's got a diameter of 20 centimeters. And it's telling us that there is a torque on this wheel of 800 newton meters. It's reminding us what the diameter is. And here's the sort of situation. So we're assuming full contact and no slippage. So, in other words, the force is all going where it's meant to be going. What's the force of the wheel on the road? So we know that torque is equal to force multiplied by distance, right? But we're not trying to find torque, we're trying to find force. So let's divide both sides by distance and rewrite our equation as force is equal to torque over distance, right? So what's our torque? We know that our torque is 800 newton meters. And we know that our distance, well, we can figure that out, right? So torque, if this is a torque on a wheel, the torque is being applied at the axle of that wheel. And so the distance from where the force is being applied, where the torque is, to where the force is being applied is actually the radius of this wheel. It is not the diameter. So the distance in this case is 10 centimeters. And that, because we should always be in this subject converting to meters, it just makes things so much easier, is 0.1 meters. So 800 newton meters divided by 0.1 is going to give you 8,000 newtons. All right, so that is the force of the wheel on the road. All right, moving on. Okay, so here's a pretty classic leverage question or lever question as a wheelbarrow. Now, the first thing I do when I look at when I look at a lever problem, is I try and figure out, okay, what class of lever am I looking at? So let's go, here's the fulcrum, here's the load, here's the effort, right? So we know those things. Now, what do we know? We know that the distance from the fulcrum to the load, which we call the distance of the load, is equal to 600 millimeters or 0.6 meters. And we know that the distance from the fulcrum to the effort, is equal to 600 mil plus 1200 mil. So that's 1800 millimeters or 1.8 meters, right? Really important when you're doing these questions that you identify your distance of the load and your distance of the effort from the fulcrum, because sometimes they'll put measurements in like this, which is designed to trick you. All right, so now what's the question actually asking? What's the force required to balance the system shown above? Okay, so if we're balancing the system, it means the force of the load and the force of the effort are equal. And so to solve that, we can use the law of the lever. Now, the law of the lever, I'm going to take a little bit longer than I would if I were actually answering this question. So torque is equal to force by distance, right? If we think about the torque from the fulcrum to the load and the torque from the fulcrum to the effort, if those are the same, if they're balanced, then the torque, we could call this torque load, and we could call this torque effort, would be equal. So we rewrite this as what's called the law of the lever. So the law of the lever is the force of the load multiplied by the distance of the load is equal to the force of the effort multiplied by the distance to the effort. Right? Now, what do we know? We know force of the load. So force of the load is 800 newtons. We know the distance of the load. We know the distance of the effort. The only thing that we don't know is the force of the effort. This is our unknown here. So we can solve this, or we can rearrange this equation by just dividing both sides by the distance of the effort. Cancel these terms and rewrite this equation as the force of the effort is equal to the force of the load multiplied by the distance of the load divided by the distance of the effort, which is going to be, what have we got? We've got 800 newtons. That's the force of our load. We've got 0.6 meters. And we are dividing all of that by 1.8 meters. And working that out is going to be, that is going to be, you know my mental arithmetic is really poor. That's going to be 266.67 newtons. Right. And that, you know, if we think about this, you know, without even doing any maths, we can just look at this and go, okay, so the distance of the load is 1/3 the distance of the effort, or the distance of the effort is 3 times greater than the distance of the load. So this is going to give us a mechanical advantage of 3 to 1. So we're going to put in, for every, you know, 1 unit of effort we put in, we're going to get 3 units of effort out. Conversely, if we've got, you know, 3 units of load here, we only need 1 unit of effort to sort of balance that. And so we need 1/3 of this load force to sort of balance this system. Right, what do we got now? We've got a bolt, and it has a pitch. And I'll go through and I'll explain what we mean when we talk about pitch. So if we think about what a bolt really is, or a screw, it's really a wedge. That is a really, really, really badly drawn wedge. It's really a wedge, right, that is wrapped around a cylinder. And the pitch, what that's telling you is how much distance does this slope move through per rotation, or per, you know, revolution of that cylinder. And that is, you know, given in some sort of measurement. And in this case, it's 1 millimeter, right? So what this means is that when the bolt turns once, right, you've moved from here to here, and that distance is 1 millimeter. And so you've also moved the bolt 1 millimeter, right? Now, let's talk about what the question's actually asking. So the bolt is tightened 1/2 of a turn, or 180 degrees, after first contact with the parts to be fastened. So what this is telling us is that we've got one thing over here, and let's just sort of draw something in cross section. So let's say we've got one metal plate, and we are fixing that to another metal plate, and that's going into sort of a threaded hole, right? And these pieces have made contact, right? They're all snugged up against one another. Now, if we turn this bolt 1/2 rotation, we have moved this thread half of the pitch, because we've moved it 1/2 rotation, so we've moved it half the pitch. So we've put, we've moved this 1/2 or 0.5 of a mil, right? Now, what's happened here? If this has moved 0.5 of a mil, but these parts are all, you know, pushed up against one another, something has deformed, right? Something's deformed in order to allow that to happen, because, you know, otherwise it just wouldn't work, right? This bolt has to go, these plates, they have to go somewhere. And so what's happening in this scenario is that the shank of the bolt is actually stretching, right? And we assume that it's stretching in this example because that's what it's told us. It hasn't told us that this other material is compressing. It hasn't told us that this bolt head is biting into this metal and actually removing some of the metal, although it should have a washer there. But that's neither here nor there for this example. Right, so it's stretching the shank of the bolt. And it's stretching it half the pitch, because it's rotated, you know, half a turn, and the pitch is 1 millimeter, so it's 5 millimeters. I hope that makes sense. Right. Lucky last for this example is this, and I don't actually have the question for this because I may not work all the way through it. I just want to sort of talk about it. So let's have a look at what's going on here. So this is some sort of linkage, and let's draw this to sort of try and simplify it just a little bit. So let's start from this end. We've got a fixed pivot here. So if it's a fixed pivot, it's probably our fulcrum, right? We've got some sort of, thing, link coming out from here. And so let's just assume that this is our load. And we've got a point at which something happens to what we're now realizing is a lever. So let's call this an effort. So what have we got? We've got a lever that has a fulcrum. It's got a load. Load. And it's got an effort. Right, it's connected to another lever. This lever, well, we've got applied force here, so that's going to be our effort. We've got a fixed pivot, so that's going to be our fulcrum. And we've got a point here where it is acting on something else, so let's call that our load. So this lever down here is connected to this lever up here. And this lever up here looks like this. Fulcrum, effort, load, right? And so, I don't know, this question could ask a whole bunch of things. It could ask, what's the combined mechanical advantage of this linkage system, assuming no, sort of energy lost in deformation of the links or friction between the various sort of moving parts and all that sort of stuff, which the question would probably do, right? So let's have a look. We've got some values here as well, which is nice. So we've got 10 centimeters from the effort to the fulcrum, and I'm going to write those as meters. So 0.1, 0.1, and then very conveniently, 0.1 and 0.1 over here. All right, so let's also look at what kinds of levers we're working with here. So effort, fulcrum in the middle, load at the other end. This one here is a first class lever. And this one down here, fulcrum, load in the middle, effort up one end. This one here is a second class lever. So let's look at the mechanical advantages on this particular lever system. So this first class lever, the distance of the effort, that's the distance from the effort to the fulcrum, and the distance of the load, that's the distance from the load to the fulcrum, are the same, right? They're both 0.1 meters. So this actually doesn't give you, or it gives you a mechanical advantage of 1, which is to say, for every unit of force you put in, you get a unit of force out. It's not a multiplier, right? It's just 1. Cool. This one here, so let's look at this. So the distance of our load is, in this case, 0.1, because we've got fulcrum to load, that's 0.1. But the distance of the effort is from the fulcrum to the effort up here. So that is actually 0.2. So we've got our distance of our effort is twice as long as the distance of our load. So this lever here is giving us a mechanical advantage of 2, or 2 to 1. Right? So the total mechanical advantage of this system is the mechanical advantage of this first lever, which is 1, multiplied by the mechanical advantage of this second lever, which is 2. So our combined mechanical advantage is 2, right? Or 2 to 1. Now, if this lever here gave you a mechanical advantage greater than 1, say it gave you, well, let's just extend this. Say this was now 0.2, right? This is now giving you a mechanical advantage of 2 to 1. So mechanical advantage of 2 multiplied by a mechanical advantage of 2. This situation here would give you a mechanical advantage of 4. And that's the way that you sort of work when you're combining sort of linkages and different parts of a system that have different mechanical advantages together. You break them apart and you go, okay, so this part has this sort of mechanical advantage. So if we have this input force, it's going to become this as an output force, and then that goes into the next sort of piece of the linkage or system, and that has its own mechanical advantage, and so that acts on that force to either increase or decrease it depending on the mechanical advantage. So I don't actually recall off the top of my head what questions are being asked here, but I imagine it's saying, if you put in this sort of force, if you put in a given force here, what do you get out at the other end? And things of this nature. So go back, have another go at that levers and torque quiz, and keep doing it until you get the questions right. Right? And if you've done it 3 or 4 times and you really can't get the question right, then shoot me a message and say, okay, so here's the one I'm still struggling with. Could you walk me through it? And I will do that. Cool. Good luck, folks.